Hi, I'm Randolph Settgast from Lawrence Livermore. I'm here on behalf of our team of developers, which is quite sizable at this point. We'll just call them the GEOSX team. I'll give you a list of names in a minute. So GEOSX is an open source multi-physics simulator platform focused on subsurface applications. It's got an LGPL 2.1 license. It's effectively, at this point, the result of a partnership between Lawrence Livermore, which is funded through ECP, in a joint project with LBL, coupling GEOSX to Chombo Crunch flow, but that's a different topic. Total Energies in Stanford. We support an open community of about maybe like 40 scientists and developers now from multiple institutions, Lawrence Livermore, Total, Stanford, University of Padova, which Andrea Franceschini used to be at Stanford, INRIA, et cetera. And so one of the major goals is obviously ease the transition of current simulation capabilities to current and exascale architectures and beyond, utilizing platform portability tools. So GEOS was the older code. We've rewritten in this new form with the express goal of platform portability. Our target applications are extensive at this point. The old GEOS was really just a hydrofrac simulator. So now we're doing main applications are really carbon storage. Sub-applications would be conventional oil and gas, seismic imaging, and unconventionals. So we have, I say it's a multi-physics code, so we have multiple single physics packages which get tested on their own. So, just running through solid mechanics, fluid flow for single phase or compositional multi-phase, in porous media and fracture. We obviously do fracture mechanics as well. We have grid-aligned fractures, embedded methods, cutting through elements, and currently doing a multi-level phase field approach to do fracture at the tip at a high resolution with a background embedded grid. Contact enforcement, this is useful for slip along faults, the pressurized faults. We have well models, prop and transport, and we're currently working on thermal and reactive transport. Currently, we have coupled physics packages working for pore mechanics, so that's solid mechanics, flow and fractures, and porous materials. Reservoir simulator, which is the previous pore mechanics solver plus wells, and hydraulic fracturing, which is pore mechanics and fracture mechanics. I label the fracture flow as pore mechanics because essentially they're the same. The solver has the same structure. Our primary target platforms are these guys. So our first target platform, or I guess the platform we're getting graded on in the ECP project is Frontier. We also have efforts to run on Lawrence Livermore's LCAP and NERSC Perlmutter. So Frontier and LCAP are AMD, Perlmutter's NVIDIA, ALCF's Aurora is Intel, and obviously we have sort of our legacy systems now, which are the NVIDIA V100 systems with IBM that are deployed at Lawrence Livermore and Total Energies. There's a little bit of a rumbling to do cloud HPC, but that's maybe not our top priority. A brief overview of the code. It's C++ 14, pretty strict C++ 14. We're going to transition to 17, pending compiler support on exascale systems. We make heavy use of templating, generic lambdas, variadic lambdas, all the little fun features of C++ 14. Data is typically managed on a mesh-based data structure built on a generic repository. So we essentially have a mesh object or a mesh hierarchy. We store all of our array fields on those mesh objects and all the inter-object relationships. Now, the inter-object relationships are really only important for very specific physics, but we generate all of them and keep them around just in case. We use Hyper for preconditioners and iterative linear solvers. And we are developing a Python front end, which we hope to serve as the primary interface for the computational components of GeoSX in the future. Our portability models essentially relies on two things. It's Lawrence Livermore's Raja platform portability layer. So this gives us portable kernel launching across platforms, tools to write portable kernels and various portability tools. So that's atomics, reductions, local array / shared memory, going back and forth between the two, whether or not shared memory is available. They have backends for OMP, CUDA, HIP, SYCL, whatever else comes along. So this is sort of stuff that we're not responsible. We just sort of piggyback on their efforts. We have portable data layouts using our own LV array class, which piggybacks on a library called Chai. And essentially, the gist of this is that as you execute Raja kernels and you capture LV array views to your data, the data will automatically move back and forth between host and device, which is great, potentially dangerous and slow if you're not paying attention. So just to give a quick example of I don't know if we were supposed to show code in talks like this, but unfortunately I did. A simple example for use of Raja in GeoSX. So we grab data from the mesh. So these are sort of mesh objects. We get a view to these data, and these are essentially array objects. Here's just a simple everything got moved over. Yeah. Here's a simple for loop, which you can see is this Raja for all. And what this is essentially a lambda that's captured in this Raja for all call, and it executes like a kernel launch, or it is a kernel launch. We select the kernel by this parallel device policy, which is improperly boxed somehow. And somewhere else in the code, there's often a header. Down at the bottom, you could see that we would define this policy as a CUDA execution policy if we're using CUDA. And if it's HIP, there would be a HIP execution policy. And if it's OpenMP, there would be an OpenMP execution policy. So the capability development in Geos for a developer. So we seek to allow domain scientists to focus on domain science and numerical method development and not computer science. This is mainly done through our physics solver packages, which really consist of four things. Data registration. So what arrays do you need to run your problem? How do you initialize the data? How do you essentially enforce the constraints? So that's assembly kernels and solution strategies and constitutive updates, et cetera. As a note, when we write things in GeoSX, we generally do full coupling. We make the full block. So if this is a block matrix at the bottom, this is a block system. We fill all the blocks. We fill all the coupling blocks, and whether or not we use them in solution strategy, we may use them. We typically run everything fully coupled right now, but there are cases where you would want to do split operators or things like that for speed. Show a quick example. How am I doing on time? Sorry. I don't have a timer. 10 minutes. 10 minutes, okay. So I'm just going to show a quick example of some preliminary runs for our ECP subsurface stretch goal problem, which is a wellbore integrity problem. So this problem will involve fully coupled physics between mechanics, compositional multi-phase flow, reactive transport, geochemistry, and fracture mechanics. The goal of this, now this is not a exascale problem itself. The goal of this is essentially in a suite of runs where you're doing a storage site risk assessment, that would be the exascale problem that is composed of much smaller problems. Or we could use this problem potentially to to calibrate reduced order models to then do a storage site risk assessment. So this is a scaling study, a weak scaling study, in which is a node-to-node comparison for quasi-static mechanics. Do I have a pointer? I kind of do, and it doesn't work on the screen. Okay. So this scaling study goes from about 8 million cells, or I'm sorry, 3 million cells to 1.3 billion cells. That's about, for mechanics, that's about 4 billion degrees of freedom at the top. In this top box, we have our Xeon reference system. And in the bottom box, we have our V100 system. And so the thing to note, this is just for the linear solve portion of it. So I'll be talking about the linear solve portion of it, which is really Hyper's performance, not GEOSX's performance at this point. So we can see that in a weak scaling study, you want all these numbers to be the same as you go up. You can see that they remain same for a little while, and then right about 4 billion degrees of freedom, we get a pretty drastic degradation in performance. And if we look at setup time versus solve time, what this is an algebraic multigrid preconditioner. So setup time is essentially the set time to set up the algebraic multigrid preconditioner once you have the matrix formed. And you can see that it is actually a significant portion of the time as opposed to the solve time, which is the Krylov iterative solver. You can see that the time goes up, and then you got this great performance down here for the Krylov solver, but it's a little bit sketchy on how well this is going to scale past 4 billion cells. Oh, sorry. One thing I forgot to clarify was on the V100 systems, we are using 1 GPU per rank. So this is essentially 1,000 GPUs, 1,000 ranks, okay? So that was for solid mechanics for compositional multi-phase flow. It looks a little bit better, I think. It's still not great. We still have a scaling problem at about 1.2 billion degrees of freedom. So we haven't pushed it much further than that as of yet. But at any rate, so those are just to give some context for the next statement. So concerns about running AMG. So I would say that there's portability, performance, and scaling of AMG setup times is of a concern. The scaling of the Krylov solvers once the AMG set up seems okay, but it's still not nice and flat like you like to see. And in general, like your matrix storage is your primary limiter for problem size. As a side project, we're doing a risk mitigation experiment on doing a matrix-free approach, which is how all the high-order finite element codes work these days in the ECP. We're talking. So this is a typical AMG V cycle. So you would start up here, and then you would have some algebraic coarsening and do a smoother here, and algebraic coarsening and doing a smoother here. And what we would do is probably just build all of these grids physically as meshed discretizations and run physics on each grid, and then do a restriction and prolongation between them and smoothing operations on the coarse grid and back and forth, instead of relying on having the matrix and then working with the matrix to form the algebraic preconditioner, which is inherently a serial process. Not inherently a serial. It is a process that is difficult to scale, let's say. So that brings us the burden back onto GEOSX. Sorry, time? How much time? 4 minutes. Okay. So we'll quickly go over our kernel optimization strategy within GEOS. So we will be on the hook now for, in this matrix-free approach, to provide fast residual evaluations and fast smoothing operators. We no longer have to fill a matrix or use a matrix or store a matrix or anything like that. So our kernel functions and classes for the code, and this is akin to like an explicit time integrator, so a wave propagation problem, if you will. So our kernel functions and classes are templated on things like number of node quadrature points and constitutive model type. The reason for this is to get the compiler the maximum information possible so that it can do the optimization as best as it can. Now, this leads to sort of a little bit of a problem where we have all this template instantiations, and we, as a temporary solution to this, we sort of instantiate all of our templates through runtime dispatch. So it's essentially a glorified case switch block, where every variant in the dispatch, you have to compile every variant in the dispatch, and that leads to long compile times. We have a comprehensive JIT strategy in development, which is going to cut this off and sort of give us a little more scalability in terms of our compile times. It's not terribly prohibitive. I think to compile on our V100 machines, a couple of the physics solvers take like a couple minutes, something maybe 3 or 4 minutes. And we rely heavily on our flexible data layouts and platform portability concepts in Raja. So when I say flexible data layouts, that's essentially how the data is laid out in memory. It's the classic CPU, you want array of objects, and on the GPU, you want object of array type of things. So this is a typical class that wraps our kernels, and it would be templated on constitutive type. And you can see we sort of we create an object that is this wrapper that wraps all our constitutive data and constitutive algorithms. And so everything that's instantiated in this class knows what constitutive type it is actually supposed to be working on. Also finite element type, so this is all the numbers of degrees of freedom, number of nodes, what the finite element operations are in reality. So within this, there would be an actual kernel update where you would actually know the size of any temporary arrays you needed to have. So your data is actually known, your stack data is actually known at compile time. All these boxes are offset. They should be shifted left a little bit. So these are all things having to do with the finite element type. And so all the finite element operations are inlined for the kernel, and the constitutive update can be inlined as well. So this is essentially in this case, let's say the CUDA compiler gets all of this stuff inlined, and it knows exactly what it has to deal with to optimize the kernel. So there's no calls to any functions that it doesn't know what function it's calling. This gets called in a simple for loop, a simple for launch, and so that would be this. That was the function we were just looking at. So it's just a call within the kernel launch. This is for a simple case, low order finite elements. If you use high order finite elements, you have to thread on. We're threading on elements. You have to thread on like quadrature points, and you share memory to bring in data and to share the data amongst the quadrature points. But it's more complicated. So the kind of performance we get when we do this sort of thing, we look at another comparison between a Xeon node and a 36-thread Xeon node and a single node of Lassen, which is 4 voltas. We get essentially an 80x speed up. Now this is cheating because we've changed the algorithm a little bit on the GPU, because on the GPU you you calculate things, you recalculate things that compile at runtime that on the CPU that you would actually store in memory. So it's not an apples to apples comparison, but ADX ain't bad. If we look at a roof line, this gets us about 6 teraflops or 5.8 teraflops, which on a 7 teraflop card is pretty good for unstructured finite elements. You wouldn't expect it to get that good of a result, but it's quite optimizable. And over here on this side, this is a weak scaling study for full runs. So you can see that we are getting, the gray line is our element kernels, and the blue line is our MPI communications. So we have an effort to try to hide communications. It is not entirely hideable. You have packing operations and unpacking operations aside from the actual communication wait times, which you really can't get around. Now, they can be asynchronously launched, but you still have to do some waiting. That's the way it goes. Ongoing work. Like I said, we're working on thermal and reactive transport. We are working on, fully coupled deformation, contact slip, fluid flow, thermal, reactive transport, fracture propagation, solver. All of this is being tested on the exascale early access machines. So right now, we're mainly concerned with the Frontier early access machine, which is an AMD machine. We're continuing work on improving our matrix-based MGR preconditioning coupled multiphysics solvers in Hyper. At the same time, evaluating multi-discretization matrix-free geometric multigrid. In the near future, as we start to get these really, really fat kernels, you notice that I was grabbing individual arrays within these kernels, which actually, if you're grabbing a lot of individual data arrays, it does bloat the register usage. So we're going to have to figure out a way to compact all of our data into maybe all of our similarly strided data into a single data array and access those within the kernel to reduce register pressure. If you want to find more information, we have a website, geosx.org. You can go to the GitHub page. You can go to our Read the Docs organization, or Read the Docs documentation. The first link will get you to the other two. And these are links for all the other tools we use.
Okay, maybe we have a question, time for one question.
I have two questions, they're kind of related. You mentioned the memory footprint problem. Can you quantify the amount of memory that the simulator is using per degree of freedom or per cell?
Not off the top of my head.
Okay. But, my second question is, you mentioned the Jacobian-less approach.
Yeah.
How are you planning to precondition?
Oh, well, it will be preconditioning on the course levels. So at each course level, we'll run a smoother. And that's the precondition, right? AMG is essentially, you have a course level preconditioner for the fine level.
Okay, so you still need, let's call it stiffness matrix for it, right? Or you just assume uniform properties?
Well, we need a stiffness matrix at the courses level because we'll need an actual solve at the courses level.
But for this, you need the stiffness matrix for the fine level, right?
No.
So you assume uniform properties then?
No. No, it's an upscaling. You'll have an upscaled grid that you're smoothing on, and then at the courses level, you'll actually have to do an actual solve. So the rest of them are just smoothers and Krylov methods, right? So.
Thank you.